Okay, so far we have discussed about how to model a system as a deterministic Kripke structure. That was in my first video. Then I talked about how to express the requirements of a system in terms of linear temporal logic. That was in the second video of this series. And finally, in the third video, in the previous video, I showed how to install the NuSMV model checker on a Windows machine. And today in this video I am going to tell you about how to code the modeling formalism which we discussed in the first video in the NuSMV model checker. Okay, so to model up the 2-bit shift register in the new SMV syntax, we will be using a few reserve words. One of them is the module main reserve word. So this just tells NuSMV where to begin executing the NuSMV code. It's just like the main function in C++ or Java. Then we make use of another reserve word, which is the var reserve word. It it is actually used to declare the state variables. Then we make use of another reserve word, the assign reserve word. So this is basically used to assign values to certain variables. And the init reserve word, this one is used to assign values in the initial state of the model, which we to variables in the initial state in the model, which we declare in the var section. Then, as we discussed, that there are two functions. One of them is the transition function, which we denote by a delta, and the output function, which we denote by a lambda. So both of those will be coded up in terms of this next function, which basically tells what is going to be the value of a next state given a certain current state and the input symbol read from that state. And if it is the output function, then it will tell us the next state bit value for a particular bit in the current state. So that is how we are going to code up the deterministic Kripke structure in the NuSMV syntax. And these two words, case and ESAC, these are just used to tell the NuSMV that a specific next block is starting inside this case block, and ESAC is the way to tell NuSMV that the case block has ended. Okay, so now we are in a position to code the model we have been discussing in the last couple of videos. You can see it on the right part of the screen here. So you see 4 states A, B, C and D, and each state have 2 bits on it. The first state A has 2 bits, 0 0, B has 1 0, C has 0 1, and D has 1 1. On the top you see the mathematical definition that states that Q has values A, B, C and D. The input symbol set has values 0 and 1. The initial state is A, and the transition function definition is also mentioned. Q cross sigma is mapped to Q, and output function lambda is also given, that it maps the states to a boolean bit vector of length k. In this case the k is equal to 2, so each state has 2 bits on it. On the left you can see the model already I have coded up for you in NuSMV. On the top you just see the module main, which I discussed on the previous slide. This just tells NuSMV that to where to start the execution of the code. Then I have used a few variable declarations in this section, the coming section, following the var. So we have these 2 bits which appear in the diagram on each state, so we declare them to be of boolean type. Then we have this enumeration type, in which we mention the 4 states A, B, C and D. And then we have this input type, which we are reading from each state, 1s and 0s. That can be true or it can be false. So now we have done the state part. and the input symbol part in the mathematical definition that is mentioned on the top right of the slide. In the next part, we need to cover the part q not equal to a. We have to assign values whatever is given in state A. In this case, we make use of this assign reserve word, and further we use the init reserve word to tell is going to be state A, which is our initial state in the diagram. And that by again making the init reserve word twice, we tell NuSMV that bit 1 is initially going to be false in state A, and bit 2 is also false in state A, and all the statements, as you can see, other than the reserve word so far, are going to be terminated by a semicolon. And if you just to mention that the declaration of variable is a little bit different, as you might have seen in Java or C++. Here we declare the variable by first mentioning the name of the variable and then using a colon sign, and then we tell it NuSMV the type of the variable, and we terminate that by a semicolon. So in the var section, all these bit 1, bit 2, state and input are all the variables, followed by a colon, and then the next is the type of the variable. So once we have assigned the initial values for the initial state, then we are in a position now to complete the transition function delta, which we mentioned here, this part. So we need to do to complete the transition for each of these. So we have 4 states and 2 input symbols. It means q cross sigma is going to have 8 tuples or rows. So we do that by making use of this next function. So here the word state is telling that this specific next is going to capture the next state values for each state. For example, if we are in state A and we read an input true, so I can tell you, or you can see it from the diagram, if I read an A and read 1 from A, I go to state B. So that is the next state mentioned in the code here. Similarly, if we are in state A and we read input B equal to false, that is 0 in our case, then the next state of this state is going to be A, as you can see from the diagram, that if we follow the 0 transition, it is going back to state A. In the same way, we have completed this whole 8 rows in our model, and then I have commented out this line. So in certain scenarios, when we are unsure about how the system is going to, for example, behave in certain situations, so when we are unsure of a certain output or a certain transition, and we cannot complete this transition or cannot make this a total function, then we use this true colon state line. Otherwise, when you know all the transition and you can clearly spell them out, then there is no need to use this line, and you can simply delete it or comment it out. Then this ESAC is telling that this case block is finished. Then I have other 2 next functions or next blocks. In this case, I put the word bit 1 inside a next parenthesis, and here you can see that if state is equal to A and input equal to true, then I tell the value of bit 1 in the next state. So if you follow the diagram, if I read 1 from state A, I go to state B, and in this case the value of bit 1 is 1, so which we model by a true value of the bit 1 variable. So that is shown in the first line of the code here. So if I read false from state A, you can see from the diagram that I go back to state A following this transition. So in that state, bit 1 is false, so give the next bit value a false. I'm sorry, I have a bit of cough. So if the state is B and input is true, now you can clearly see that it is going to state D, and in state D the value of bit 1 is true, so that is modeled by this true here. Now if the state is B and input is equal to false, you can see from the diagram that it is going to state C, and there you can see the value of bit 1 to be false. if the state is C and input is false, then you can see that it is going to state A in the diagram, and it said A, the value of first bit is false, so we just give the value false. And then in the same way we complete the first bit values for all these state and input symbol red. In the same way we have completed this bit 2 next function values, or the lambda function is encoded in this way. You can check this from the diagram, and then we use the reserved word LTL spec. This basically is used to give the linear temporal logic specification which we want to verify on the model. So I discussed about LTL specification in a couple of videos ago, and I also showed on the diagram that this property we can check manually, and we can also use this we can also check this by means of the NuSMV model checker. So here I have specified this, and as I can demonstrate it to you again, that what this property is saying is that it says whenever bit 1 is true, then in the very next state bit 2 is true. So bit 1 is true in this state and in state D. And the second part of the property is that in the next state, wherever bit 1 is true, bit 2 is true. So the next state of this state is this one. If we follow this path and this path and this path and this path, so if we follow these 4 paths, so here you have bit 2 true. So if I follow this path or this self loop, then the bit 2 is true. And if I follow this path, again bit 2 is true. And if I follow this path, again bit 2 is true. So this is how we just checked it manually. So it is also possible to check if we execute NuSMV on this code. So if you see, I have saved it as bit shift complete, and it is in a folder called video tutorial. So let's run NuSMV on this. So here just to show that whether I have this file, I have the file here. I just run the command NuSMV, and then I call the file bitshift.complete.smv, and when I hit enter, NuSMV tells me that this specification is true, as I just demonstrated you on the model. So this is how a model is verified by means of the NuSMV model checker. In the next video, I am going to tell you when the property is false, and when NuSMV gives some counterexample, how to make use of that counterexample as an interesting test case. So that is going to be the real part of this whole series of lectures. Thank you.